Hello, this is the Tepid Coder. In this video, I thought I'd kind of go back to basics for a second and compare the things that lists are good at versus vectors. So we've talked about vectors before and how you'll have something like 0 nodes, you allocate 1 node as you need it. And you're going to double it in size to get the next size when you insert a new node. Now we have 2 nodes, right? Now, when you do it again, we're going to double it in size. We currently have 2, so now we're going to have 4. So we have room for 2 more nodes, but we're only going to fill one of those. So that means the next insertion is going to essentially be free because we don't have to do an allocation. Okay, and the next time, it'll happen after we've filled 4 nodes. We're going to need enough room for 8 now. So the next 3 inserts will be free, and this first one is going to cost us because we have to do the allocation. So we have like one here. Okay, we have another one here. Another one, and another one. So there's your 4 nodes, right? Anyway, so you can imagine it kind of like this. You have like 1, then you have 2, then you have this one's filled, but that one's free. You fill this one, and we're gonna have this one filled, but these 3 are free. And then next time you're gonna have what? I guess it's going to be 7 free. It's always gonna be like 2 to the n minus 1 free, something like that, right? Anyway, that's all well and good. This is pretty fast too. Some disadvantages are when you actually need to resize the block. Sometimes the memory address you get, I call this address B in memory for this first node right here. Sometimes that address is going to need to change to somewhere else in memory where the OS can actually fit however much space you need for the new nodes you're adding, right? So it'll actually have to move everything to a new block. In order to do that, it's going to call standard copy on everything. So std : copy, right? Now, if the stuff in these nodes here that you're copying over into this new block of memory is trivially copyable, like it's a primitive, like an int or a short or a double or whatever, maybe it's just like a pointer to something, it's just going to basically call memcopy, right? Standard copy is just going to use a memcopy. Otherwise, it's going to have to use the copy construct for everything. And every single one of these nodes here is going to be copied one at a time in that case, which is pretty slow, right? And then after it's done copying, it's going to have to call the destructors for all of these nodes. These all have to destruct. Just like mark that in red or something so you can kind of imagine these all being destructed after they're copied. Okay. And then over here, what we end up with is all these nodes that were copied over, plus room for however many more nodes we just added in this new block of memory. So when this has to happen right here, this copying and destruction from the old block, we have a new base address now. Let's call it capital B. Or maybe call it, I don't know, B prime or something. When this has to happen, it's actually slow. Very, very slow. Now, with a list, we can avoid this ever happening. We have to have this copy. However, every single node we create has to be a new node in memory. So let's show that. So with the node, what you'll have is you'll have a block like this. That's the allocator of the node. It's going to have a P for previous, which is going to point to nothing. There's no previous node, it's your first node. You'll have an N for next node, right? This is going to point to some other block somewhere in memory, which also has a previous and a next, right? Next goes to some other node. So over here, we have previous, we have next. Maybe this one points to 0 because there's no next node. This previous points over here to throw this block. This previous points to throw this block right here. So every node basically points to the next or previous in the chain. You can have it just point in one direction where it's a singly linked node, where it only points forward. That's completely fine too. But I think the way you'd have this set up in a standard list would be a doubly linked list. So something to think about this is every single node has to be allocated as you need it. So that's really slow. Allocations are super slow. The other thing to think about is when you copy things or traverse the list, you're basically going to say start at some address B, right? Let's say this first node is your base node, is address B. If you want to go to the next node, you have to say, okay, jump ahead, offset bytes in memory, right? And that's going to give you the position of this next node pointer, right? And then you use that pointer, let's say you dereference it and get the value at that pointer, that is the address of this next node over here, right? And you can imagine every single time we're doing this dereference thing. We're checking the address at the top of the structure, plus some offset, and getting the address stored at that offset in the next pointer. And then we use that address to do a lookup, and we get this node right here, right? Then we do the same thing again for this node. We'll have like the base address of this, node, right? N plus offset to that next one, right? We dereference that, and we hop to some other location in memory, right? That's actually really slow. With a vector, everything is contiguous. So if you want to find the next node, like the nth node, right? Nth node is just going to be your base node address plus the size of an element e times n, right? So b plus size of each element times number of nodes for the offset, right? So here's 0, here's 1, here's 2, here's n. So that's how you're getting this address. You can jump straight to it. So it's quicker to traverse a vector to actually do operations on it. It's also going to have better cache locality, which means if you're looking this up right here, you might also get like these two for free if the nodes are small enough. They might be in the same cache line. So it ends up being way faster to do operations on it. So something that's an advantage of a list, though, is that if I delete an element in this vector, see I delete element n right here that I mentioned. I want to delete this one. What I would actually have to do is I would have to look at all of the elements below that, and I would have to copy them up, right? And then what I'd have at the bottom is this little hole, which we're not going to fill. It's just like free space. Let's say free, free space, right? That's what you would do when you free in a vector. So you incur the cost of copying everything past the point you deleted over top of the element that you deleted. So that's kind of slow to delete. With a linked list, what you do is you basically say, imagine I want to delete this node right here, right? What we're going to do now is instead of having the stuff point to it, we're basically just going to unlink it from the chain. We'll call the destructor on it, and we'll say this now points over here, and this previous one now points up here, right? And no matter how many you delete, you just look at the node before the deletion point and the node after the deletion point, and you just set the next of the previous to the node after the range, and you set the previous to the node after the range to the node before the range. So it's really quick to do that. And it's not going to take more time as there's more nodes being deleted. It's just a constant time operation. So with a vector, the more nodes you have to copy back to the point where you deleted, the longer it's going to take. Especially if the data isn't trivially copyable. You might have to do some kind of like a copy constructor for each one. Okay, and it's also possible that some types of things you store in a vector might not be copyable. You'd have to like move them or something. And if it doesn't have a move constructor, maybe you can't do it, right? Maybe it has to use the copy constructor and it's extra slow. Basically, it's going to take longer the more elements there are after the deletion point in a vector, whereas for a list, it's going to be constant time, so it should be super fast. Okay, but traversing the list and actually doing operations on the list is going to be slow. So I made a quick project to kind of benchmark the speed of doing a bunch of insertions into a list versus a vector. So I want to kind of go through that real quick. What we're going to have is a node that we're inserting. It's going to contain a standard string. So I'm kind of hoping that makes it not trivially copyable. And then I'm inserting a double, which is a primitive type, and a signed 64-bit integer, which is also a primitive type. I'm giving these both default values. Now what I'm doing for the list test is I'm basically inserting 1,000,000 nodes. And every single time I insert a node, I'm increasing the value of the number by 7. I'm decreasing the value of the double by whatever the current iteration is divided by the smallest possible value I can reliably represent with a double. I'm just doing things with it each loop. And the reason for that is if I just use the same value each time, it can actually optimize the code out. And I don't want it to optimize my code. I want it to be doing stuff every single time. I'm also converting the string to be whatever the string representation of the current loop iteration is from 0 up to 999,999 is. Okay, and I'm storing that. And then I push that into the list. So it's going to be 1,000,000 nodes in there. It's going to have all that junk data. It takes a timestamp before, a timestamp after, and it's going to measure that elapsed time in milliseconds and print that out. I do the same thing with a vector, but I'm going to reserve all the space that I need. So the cool thing about a vector is you can actually say, I need exactly 10 nodes or whatever. Here we go. You can imagine there's like 10 in here. I'm not going to draw it all 10, but you know, whatever. 10 nodes, right? Here's your node 9, here's your node 0. You can allocate enough space for that all at once, whereas with a list, you have to allocate each node one at a time, which is going to be slower. However, if I didn't do that, it would do the thing I said first, where you have like 0 nodes, and you have 1, then you have 2, then you have 4, then 8, and 16, ... And eventually, maybe you get to 16, it's like, oh, I can't use the same base address. I have to copy all this stuff to a new base address, right? And then we're copying all that stuff over there, plus we have this extra block now with some more nodes that we don't have to allocate. So it's kind of a trade-off between having to allocate every single node, but also not having to allocate every single node, because we can allocate a couple in batch every once in a while. But at the same time, we also have to incur the cost of copying everything over sometimes when we can't allocate contiguous blocks of memory that are large enough for what we need at the same address. So it's kind of a trade-off back and forth. And you'll see that if I don't reserve all the nodes I need, like if I know I need a million at once, it's going to actually end up maybe favoring the list sometimes. So I want to show that. Let's first not reserve the memory I take, and make it allocate 1, then 2, then 4, whatever algorithm it's going to use for determining the next size. And it's going to do those insertions. So it's kind of like for like testing here. They're both doing the exact same loop. So let's give that a try, see what we get. Okay, over here. So the list took 1,539 milliseconds, and the vector took 2,321 milliseconds. So the vector actually took longer. And that's because of the copying, I think. Let's see if it's reliable. Yeah, so it's taking 700 more milliseconds, which is like half a second, you know, a little more than half a second. Here it's taking 800 more milliseconds, looks like. It's about a whole second longer. Yeah, so pretty reliably, it's about, I don't know, 700, 800 milliseconds slower. Now if I reserve all the space I need for a million nodes, the vector should overtake the list. Okay, 1.6, and we have 1.3. So it's 300 milliseconds faster now. Okay, here it was 500 milliseconds faster. There it was about 400 milliseconds faster. So anyway, that's pretty important to know about. So basically, we have the cases of allocating each new node, which is pretty, I guess, constant in time if you're allocating one at a time for a list, although it's slow to do. For vector, you can get away with, what do I say, resizing the vector at pretty consistent speeds until it has to copy stuff to a new block of memory because it can't allocate or reallocate the block it's currently sitting in to be large enough to fit all the nodes you want. At that point, it ends up being slower. So it looks like with a million nodes with this sort of, you know, structure, it ended up being slower. Now, if I got rid of that string, I wonder, would it still be slower, though? Because maybe it'd be trivially copyable, right? In that case, I would expect vector, even without reserving, to overtake the list. Let's see if I'm right. You know, it's important to be kind of scientific about this and run some tests. Look at that. Trivially copyable. They both went a lot faster because they're not constructing string objects, and the vector was still faster even though I wasn't reserving it. See that? Alright. This isn't a test I did before I started filming this either, just to be clear. Now let's try actually reserving. It should be even faster. So I was seeing like 90 milliseconds before. What is it now? 103. Oh, it's actually slower that time. 101. 86 was quicker that time. Huh. 88. It's about the same speed, really. A little slower even sometimes. 88. 102. 81. 100. So let's take out the reserve again. I'm seeing 80 to 100. Maybe I didn't run enough tests, you know? So we have 93, same range. 112 was longer. 102. 82. 92. 99. 80. 107. 107. 80. It looks like it's really about the same, but I am seeing up to 110 and stuff if I don't reserve. It seems like the high time is longer, but the load time might be lower or the same. I don't think I saw any 80s with reserving. Let's see if I can get that low. Oh, well, the first run did. 75. So, yeah. This is slightly faster. And I think it's more consistently faster, but not by much. 106, that was pretty slow there. 83. 69, that's even better. That's the best yet. 86. 93. 105. 101. 69. 87, yeah. Anyway, it's important though about this stuff. And I kind of want to show a test with deletion. There's a couple cases. It could be the case that I want to delete and I know right away what the address of the node I want to delete is. Maybe I'm holding iterators to each address in the list. Maybe something like a deck might do something like that internally, because it has random lookup. For vector, I can easily just delete from some node to some other node, any range I want. Maybe I could do like 50,000 deletes within the million, and I can see just exactly how long that takes. And I could do the same thing with the list, but the problem is the access time to find the nth node up to the mth node, let's say, is going to be longer. So I'm not even sure that it'd be a fair test. If I delete from the beginning of the list and the beginning of the vector, that's also kind of not fair to the vector, though, because the vector is going to have to copy everything from the point of deletion back to the beginning. So I'm not sure how to do this fair and make it like an average case. If I do the middle of the list is going to suffer because it has to do the lookup time to find the node to delete. Whereas if I do it at the beginning of the vector and list, then the vector has to copy more elements, which is unfair. And if I do it at the end of both, obviously it's worst case for the list and best case for the vector. So I could maybe show those real quick. Let's I don't know, I'll do this. I'll say for size t sti equals 0, size ti less than, say 100 sti. That's not going to be, I'm going to have to say like 50,000, 40,000, whatever. Let's say vec.erase, vec.begin, plus, I don't know, random modulo 50,000. Yeah, I'm only erasing one element each time. Now here, I think I want to do both cases. I'm going to do random. I'm going to do from the end of the vector, which I think list has pop back, right? List pop, yeah, pop back. That'll erase the back. So let's do this. But I'm not going to do that yet, because that's not fair. I'm going to do list.erase. It's going to be list.begin. And it's going to be standard advance list begin. And I want to advance it random odd 50,000 times. Do I not have standard advance? I need algorithm, I think, for that. Let's see. Algorithm. Okay. I'm gonna have to do this. Put it in the iterator first. So standard list type t, which is node, iterator it equals, and it's going to be list.begin. Okay. And then if I do it, okay, I can erase the iterator. So it's going to have to advance however many nodes that is, from 0 to 49,909 nodes. Expect a semicolon over here. Yep, okay. So let's actually try that real quick. And keep in mind, this is going to be very slow for the list to actually do the advancing here to get to the node. Whereas for the vector, it can basically construct this iterator object and jump right to that address and just delete that one node. And also, I could be testing like ranges of nodes, like maybe I'm deleting 10 at a time. That would actually favor the list a bit, because the list, like I said, can just reattach nodes after and before the range, whereas the vector has to copy everything. But let's run this first and just try some different examples here and see how fast they run. It's taking a very long time. Yeah, 40,000 deletions for that list is super slow because of the lookups. That was over 9 seconds. It's over 9,000 milliseconds. Wonder if it's going to be slower because it has to do so much copying. This is way slower. Oh my. This also isn't a fair test of the vector because it's only the first 49,999 nodes. Well, first 50,000 include zeros, right? So, yeah, that took 45 seconds. Wow. So let's speed that up a little bit and make it more fair for the vector. Let's always just erase from the end this time. I'm going to say vec.erase. Is there a pop back? There's a pop back. So let's do that for both. Make them both pop back. This is the best case for the vector when it's deleting. Okay. But it's also going to be the best case for the list because it holds a reference to that. Ooh, the vector was faster there. Okay. Vector's consistently faster now. And what if I do pop front? This should be the worst case for a vector. Vec.pop front. vector doesn't have pop front. Not surprised it doesn't, because that's a really inefficient thing for it to do. So I'm just going to take this, paste that back in. I'm not going to add to that iterator. We're always going to race in the beginning. This is going to be super slow. Worst case scenario for the vector. I bet this takes over a minute, because we were at 45 seconds before. And some of the time it was at the 50,000th element. I was going to say index 49,999. I probably should do a test on the list where I actually advance to the last node. I could advance to size -1 because I start at the 0th node. And I could erase that node. That would be really unfair to the list. Although the fact that the list holds a front and back node reference is allowing me to do that pop back really quickly. So yeah, this took 46 seconds. Which, I mean, in the grand scheme of things, we have a million nodes. Skipping ahead 50,000 nodes sometimes isn't really going to help that much, really. It's a small percentage. So, yeah, erasing with a vector is very, very slow if it's towards the beginning of the vector and the vector is sufficiently large. So, the other thing I want to talk about, too, is that the list, the iterators to nodes in the list remain valid even when you delete things before or after them. The only thing that becomes invalid is the iterator to the specific node that was deleted. With a vector, any iterator that is on or after the node that you delete becomes invalid. So if you're holding a reference to something contained in a list, you can trust that that node is going to be a valid reference when you actually reference the underlying node instead of the iterator that points to the node, right? So I'm going to make this a little bit quicker to run real quick, get rid of this vector test. And I want to do a worst case pop back kind of situation for a list. So in order to do that, I'm going to make it actually find the last node. So let's say list begin. We're going to advance all the way to list.size -1. So that's the last node. We're going to delete that each time. Alright, that's how long it takes to run. Now, this case might seem stupid since we have a pop back function. We're always deleting the back, but it could be we're searching through the list to find something, right? And we have to touch every single node in order to get to that last node. And it could be the thing we need to delete, it just happens to be at the last node. If that happens every single time, then it's, you know, unbelievably unlucky for a list of a million nodes, but it could conceivably be the case. So I just kind of want to show the worst case of vectors and lists and maybe just have that information out there when people are considering what they're doing with the containers. Are they deleting a lot? Are they doing a lot of insertions? Can they know ahead of time how many things are going to be inserted into the container? Because if you know it's going to be a million nodes inserted, you might say, okay, well, I'll do it in a vector then. Because I know right off the cuff it's going to be a million nodes, and I'm not going to ever delete them, or if I do, it's only going to be very rarely. You know, that's a great case for a vector. I'm going to do a lot of operations on them, and I have to go from node to node constantly and do a lot of operations on each of the nodes. The lookup time is going to be way faster in the vector. And it's also going to be often in the same cache line when you're doing the operations. So if you're using this a lot, and it helps for them to be contiguous when you're doing operations, vector's great for that. If you're doing things like deleting frequently, lists are great for that. Especially if you hold references to the general areas where you need to delete things, like you hold references to like iterators or something. I should probably do another video where I compare like dex as well, not just vectors and lists, because dex lets you do random access, and I would imagine probably the way it's doing that is it's probably using something like a list in the background, and probably holding references like an array to each of the nodes so you can jump right to them. And when you delete something, it could just remove that reference, probably copy all of the references to subsequent nodes over that position, just like a vector would do when you delete something, and then the elements within the deck itself probably would get disattached, just like a list would, you know. And this list thing is still going. You can see just how slow it is to have to look up memory in order to go from node to node. So the worst case of a list, which, I mean, obviously I could just use pop back, seems to be much worse than the worst case of a vector, even with all the copying that has to happen, just because the memory is contiguous. It's not having to jump around. And I can see right here the session length is 2 minutes 35 seconds. That's how long I've been bloviating. Oh my. Do I even want to let this thing finish? It's very clear to me here that the vector has won this competition. I think it was 46 seconds when I did the worst case. And remember, the worst case is something like having to do this whole thing where you reach from the beginning, and then everything else gets pushed up. Then you reach from the beginning, and everything else gets pushed up, and so on and so forth. It did that, what, 50,000 times? So anyway, future type of coder here. The test finally finished. Yeah, it was 23 minutes that took. Oh, jeez. So yeah, if you ever have to traverse a list all the way to the end, that is how many seconds that's going to take on my CPU at least. Now, I can do something interesting with this. I can say, I'm doing this how many times? 40,000? So, I'm traversing, it would be a million minus 40,000 nodes, and then a million minus 1 minus 40,000, then a million minus 2 minus 40,000. And we will not be doing that test again. That took forever. Okay. So let's see, I have 1 million. Okay, and I have 40,000 minus whatever the current iteration is. So, what if I say this? Size t equals 0. Is ti it's less than 40, 0, 0. Is ti plus plus. Okay, and the number of nodes I need to look through. Let's say size t nodes to iterate or traverse, let's say. I like that better. I don't even need to initialize that because I'm going to assign it over here. So the nodes that you traverse are the full million minus 40,000, but then minus the ones I've already deleted. Okay. So now I want to say size t total nodes traversed equals 0, and this one is going to add that each time. Plus equals nodes to traverse. Okay. Nodes were traversed. Okay. Let's get rid of these tests for now. So that's how many nodes were traversed, allegedly. Actually, I want to copy this first. That's how many minutes it took. Elapsed minutes equals that number. So that number right here, 37 billion, 600 million, 20,000 nodes had to be traversed. If this math is right. I think I did this right. Maybe someone in the comments can let me know. So if I did that many in this many minutes, that's how many nodes per minute. So double nodes traversed per minute equals this. I should probably cast that to a double. Okay, and I'm going to say standard cout double nodes traversed per minute. Okay. Nodes per minute. Yeah, that's scientific notation there. That times 10 to the 9, okay. I don't want that in scientific notation though. I'm going to do standard print. F. I want to say 0.2f. Yeah, I'll just do F. Yeah. Nodes were traversed per minute. Come on. Okay. Okay. Let's divide this up a little bit so I can read it. 1,627,781,445.4 nodes per minute. I'll just say 1.6 billion nodes per minute. So 1.6 billion nodes per minute can be traversed on my i7 8700K CPU. So one other thing I'm kind of curious about now, before I end this video, is I want to check exactly how many times the base address had to be moved. Like how many times we triggered a copy. So when I'm pushing back here, what I kind of want to see is what's the old and what's the new address. So I do node pointer let's say LP node. Okay. What I want to say is, let's be 0. I'm going to call this previous node. Okay. If LP previous node, then if LP previous node not equals vec dot, let's say vec 0 reference. So the reference to the first element. So if the reference to the first element is changed, let me trigger a copy. So I'm going to say size t, let's say vector, let's just say copies equals 0 to start with. Okay. How many times did we have to move the entire block of memory to a new address in order to make its elements contiguous? Okay. And over here I'm just going to say that plus plus, so we triggered a copy. And then we're going to do LP previous node is going to equal and vec 0. So you know at that address. Otherwise, previous node, is it? Yeah. In fact, I should always say the previous node is assigned to that address. Yeah. By default, it's 0. So this is going to trigger. Okay. And then we're going to assign it every time. And if it's changed since the last time I assigned it, then it's going to trigger again. Okay. So now what I want to say is, how many times is this copied? Okay. Print. The vectors base address. Vectors elements base address changed that many times. I have erase happening here, and it's always from the beginning, which is the worst case scenario. I'm gonna stop this. I'll do a pop back. That'll be a quick test. There we go. The base address changed 0 times. I don't believe that. I had that string back in there. What if I did 10 million vector copies? 6 times. Here we go. Oh, actually, I'm reserving it. So let's actually not reserve any. Okay, and then we'll just do 1 million again. I bet it triggers a ton of times now. 34 times. That's a bit bigger than I'd expect, actually. Because if I just do like log 2 of 1 million, right? Let's say 1 million. Okay. And I do log of that divided by, let's say 2, log of 2. Okay, equals 19. So I would expect like, I don't know, 19 block reallocations. At the most. That's if it had to what do I say? Copy everything to a new block every single time it reallocated. It was never able to just resize the block. And I would expect 19 times. So it must not be using a algorithm that always doubles the size. It must be something else. It must like increase logarithmically or something. I'm not sure exactly what the allocator function is and how many new nodes it allocates each time. It doesn't have room for something. Anyway, that's interesting. So I kind of want to recap everything real quick. So vectors, if you know the size you want to reserve, is really fast. And lists could be faster if you don't know how many elements you want to allocate in advance. Not necessarily, but could be and probably is with enough nodes, just because it's not having to do any copies. You can prevent having to do those copies by reserving as many as you need up in advance, right? If things are trivially copyable, the vector still ends up being faster. So that was something else I covered. Deletes from vectors are horribly slow, but deletes from lists could be even slower, because if you have to find the node each time, it ends up being towards the end of the list, and it's a sufficiently large list. You know, I was only getting, what, 1.6 billion nodes per minute could be traversed to the list, right? Whereas the vector, I jump right to the node I want in memory, because it's just the base address plus the node offset, or index I should say, times the size of each element in the vector. So Cool. Deletions, though, once you're at the node in a list, is super fast. It's constant time, no matter how many nodes you're deleting, as long as they're contiguous, rather. What else? Yeah, so allocating in list is pretty constant time. Not necessarily, but it's pretty constant time. It's just going to be one node allocated at a time. Whereas a vector, there could be a copy involved. So I think, what else? I need to mention, right, when you're doing operations on nodes in a list, you're actually traversing through, it's going to have that same like lookup speed problem right here when you're doing the work, versus like the vector having cache locality. So when you're doing operations on a large vector, it's going to end up being a lot faster to go through each of the nodes, visit them all, do some operation, and continue. And I think that's about going to do it for this video, guys. If anyone has any questions or suggestions or criticisms, I'd love to hear them. If you have any other things you'd like me to test, maybe mention those too. I'm tempted to test standard deck next, maybe. Compare those against these. But if you liked the video, give it a thumbs up, consider subscribing for more content like this, and I will catch you guys in the next one. Have a good day. Happy coding.